Hello, everyone, and welcome to NASA's Jet Propulsion Laboratory in Southern California. NASA's Perseverance rover landed on Mars on February 18th, and it's been really busy since then, completing initial checkouts and starting its science mission. I'm Jari Cook of JPL's Digital News and Media Office, and I'll be your host today as we talk about early science findings and preparations for the next major mission milestone, collecting the first ever Martian samples for planned return to Earth. So those of us here at JPL have our masks on because there's been a recent increase in coronavirus cases here in LA County. But I'm going to introduce you now to our speakers. We're going to start off at NASA headquarters. Thomas Zurbuchen, Associate Administrator for NASA's Science Mission Directorate. And then here at JPL, Jennifer Trosper, Perseverance Project Manager. Ken Farley, Perseverance Project Scientist. Vivian Sun, Perseverance Science Campaign Co-Lead. And Olivier Toupet, Perseverance Enhanced Navigation Lead. We will be taking questions during this briefing, so if you're a member of the media and you're on the phone lines, press *1 to get into the queue. And if you're on social media, use the hashtag #AskNASA. So now I'll turn it over to Thomas Zurbuchen.
Well, thank you so much. I just cannot tell you how excited I am to be here today and be part of this moment. Of course, we're starting to conduct the observations that I've been planning for years or even decades and continue to learn about this beautiful planet. The planet that has so many answers to questions that we have on our minds, such as, why does it look like it does, so dry and desolate even, and did it ever harbor life? And we're now ready for years and decades of discovery. Missions like that, of course, are planned and contemplated to the best of our ability, not only how we execute these observations, but also how it fits into our plans, not only of exploring Mars, but all the solar system, and even learning about our Earth, our home itself. And let's start with the planning that goes into the rover itself and also the journey to Jezero Crater. It's an incredible team that got us there. Frankly, I'm just such in awe still about this team. And I can't forget the amazing movies that were played back to Earth, both of cameras looking down into the dust whirling up as we were landing and cameras up, looking at the parachute going up there. And of course, that inspired me, inspired all of us, and we believe inspires future generations of explorers. All that preparation now turns into the wonderful phase that we're in now, the time that we really get a chance to observe the surrounding and learn, the time where surprises are starting to come in, and the time where we learn things about our new kind of environment of this planetary neighbor. Please, could you pull up the slide? We've, of course, used a vast Martian fleet of spacecraft to learn about whether water existed on Mars and inform us about the complex chemical composition, the geology. And we're studying the planetary crust and mantle of the core right now on InSight. And I just want to give you a heads up that even later this week, we actually have another news conference and kind of news are coming out of this InSight spacecraft about the very questions I just addressed. But today, now, we're here talking about Perseverance, going right to the exact place that can help us gather the next set of answers to key questions, then generate even more. We didn't just parachute in, of course, and try to figure out when we're on the ground. We landed in the most promising place to answer the very questions I just outlined, Jezero Crater. That used to be a lake and really the home of the most important site of Mars discovery today. We will see and discuss evidence that the lake had multiple cycles of dryness and filling back up. And Ken Farley, of course, is going to talk to us about this and also about the instruments that are kind of really showing us new things about the Mars environment, unprecedented instruments that we've never had there. Could you pull up the next visual, please? We recognize, of course, that exploration is not a sprint, it's a marathon. Perseverance is one step of a long legacy of carefully planned Mars exploration that links robotic and human exploration for the time to come. Our minds are already there with the human explorers on the surface of Mars, just like Perseverance is right now. It's also laying the groundwork for one of the most ambitious campaigns yet. And of course, that's a campaign of international collaboration with the European Space Agency and NASA, bringing back samples that are collected on the surface of Mars, bring them back to the best labs that are available to all of humanity for the analysis of the very questions I already outlined. We're just so excited to get to that phase. Every yard on the surface of Mars is a Mars of sample return. And but back to the present, of course, I just can tell you how excited I am to, with you, learn about these discoveries and really what we've achieved so far. Time and time again, this team that is really at the heart of this has exemplified immeasurable dedication and, shall I say, perseverance. I just can't wait to see what we uncover next. And I'm really excited, Jennifer Trosper, to turn it over to you, the Perseverance Project Manager. Jennifer, go ahead.
Thanks, Thomas. Well, it's great to be here to talk about Perseverance and Ingenuity and what the operations team has been up to this summer. And perhaps, like a lot of you folks, we've actually been on a road trip. This road trip is associated with our very first science campaign, and during it, we will take our very first sample from the surface of Mars. Go ahead and bring up my first graphic so I can give you a little bit of orientation about where we are. In this graphic, you can see the landing location, which is at the very top in the middle, where the beginning of the white line is. You can see the rover's current location, which is the blue dot, and you can see where we've been driving this summer on our road trip. We've been driving mostly south. You can see there's an area in the middle we call Seta, which is a lot of sand dunes, and we've been skirting the edge of those sand dunes. If you recall at landing, our terrain relative navigation system also diverted us away from those same sand dunes because they are dangerous. We don't want to drive the rover in those or we could get stuck. So we've been skirting the edge. You can see where the rover is currently in that blue dot. Then you also see a red dot. That's where Ingenuity is. We've been continuing the Ingenuity mission, and Ingenuity just recently flew across that Seta region to the south. It's in a location where the rover will eventually get to after it does sampling at the location we're currently in. So we've been doing a lot of driving. If you bring up my next graphic, please. This image was taken during a new kind of driving that we've been doing on the rover. We've been upgrading our driving to an autonomous navigation capability. So this is taken from the navigation camera, looking back over the rover after it did one of its first and longest self-directed drives. So those wheel tracks that you see in that image are all directed by the rover in its autonomous navigation. You'll hear a little bit more about that from Olivier Toupet later on the panel. So we haven't just been driving, we've actually been continuing some of our tech demos. One of our tech demos, if you recall, is MOXIE. MOXIE's purpose is to demonstrate for future missions the ability to extract oxygen from the carbon dioxide atmosphere. We've done 3 runs to date, and those have all been very successful. Each one got about 6 grams of oxygen. We will continue to do those runs throughout the seasons on Mars. The atmospheric density varies, so we want to make sure that we get experiments at the lowest and highest atmospheric density. And this mission is, and this experiment is feeding forward to these future missions that would want to extract oxygen to use for human astronauts to breathe and even launch vehicles. So congratulations to Mike Hecht and his whole team for a great experiment so far, and we'll continue to be doing the MOXIE tech demo throughout our mission. Another demo that we've been continuing is the operations demo for the Ingenuity helicopter. You recall that we continued the helicopter mission to feed forward information to future missions about how an aerial reconnaissance vehicle might help the science investigations for future missions. We just completed Flight 9. Flight 9 broke all of our records. The duration was 2 minutes and 46 seconds. The velocity was 5 meters per second, and we quadrupled the distance that we had ever flown, and we flew about 625 meters. And that's the flight that took us over to the south end of Seda. I have to say, when we were all sitting there waiting for the data to come down, we were very relieved that the helicopter succeeded on that very ambitious flight. Our next flight is planned for no earlier than 7/24, July 24th, and we'll be going to an area called the Raised Ridges, which you'll hear about from Ken and from Vivian on the panel in a little bit. It's an area where we may choose to do some sampling. The next thing that we've really been working on, probably the most since we last talked, is preparing for sampling. So I'd like to show this next video, which reminds you of our sample caching system. The purpose of our sample caching system is to acquire samples and then to transfer those through our bit carousel to the adaptive caching assembly, which is in the front of the rover. The front of the rover then has another sample handling arm, which manages those tubes and the samples inside of them to do imaging and measure the volume, and then we will seal those and store those for planned future return to Earth. So a lot of what we've been doing recently, both on Earth as well as on the vehicle, is preparing for that first sample. So we've been checking out the adaptive caching assembly, which is there in the front of the rover. One of the things that we did is we actually processed a witness tube. So we have 43 sample tubes on the rover. They're inside of the front of the rover here in this adaptive caching assembly. And 5 of those are witness tubes. The purpose of the witness tubes is exactly as they're named. They're to witness any contamination that might be present so that we can correlate that with the samples taken at the time. The specific witness tube that we actually just processed was in the bit carousel here, measuring any sort of contaminants that we have seen in the bit carousel since launch. So we extracted that with our sample handling arm, and you can go ahead and play the next video. We processed it by imaging it. So this is actually taken with a cache cam. It's a camera inside the adaptive caching assembly. It's imaging the inside of that witness tube. So inside there you see a witness tube assembly, which is what collects the contaminants. And then after we image it, we actually seal it and activate the seal. And that's what you see at the end of this video. So the great news is that all worked perfectly. And so we are ready to sample. I am very excited about getting our first sample on Mars. I think the team has done a tremendous work. I joked about it being a road trip and summer vacation. They've been working very, very hard. It hasn't really been a vacation for them. We're still working 7 days a week. But they've done the job, we're ready to go, and we expect to get that first sample within the first few weeks of August. And with that, I'd like to hand it off to Ken Farley to talk more about the rationale scientifically behind what we're doing.
Thanks, Jennifer. Indeed, it has been an extremely busy 5 months for Perseverance and for the team. Not only have we done the technology demonstrations that Jennifer described, but also testing out a lot of our capabilities and acquiring an enormous amount of scientific data. And I want to tell you a little bit about the highlights of that data, tell you about some of our discoveries, and also to tell you about some of the things we are going to be doing in the days ahead. I'll start off by talking about the current environmental conditions within Jezero Crater. Perseverance has a very sophisticated set of sensors on board to try to understand the atmospheric conditions and the climatic conditions and to relate them to the broader conditions around Mars. And we have been acquiring some really fascinating images of dust devils. Dust devils are just like on Earth. They're vortices that lift dust into the air. And we see them very commonly in images. Sometimes we see them when we have set out to do so. We point the camera in a region and at a time when we think we might see them. And occasionally they just appear in images that are taken for navigation purposes or for understanding the geology. We're getting photobombed by dust devils. We've also acquired images like this one here, which shows a wind gust sweeping across the landscape, lifting dust and blowing it along. This is a very visceral kind of image, makes it feel very Earth-like. We have this sophisticated set of instruments on the rover that we hope to better understand why this is happening and what it means for the big picture. Also within the last several months, Jennifer mentioned we're on a road trip. We've driven about 1 kilometer to the south, investigating rocks of the crater floor. So now we're looking at environments that are much further in the past, billions of years in the past. If I could have this first movie, this shows a panorama that we took of these rocks of the crater floor. These rocks are important because we believe they are the lowest down rocks in the sequence of rocks that we have, and therefore they are very likely to be the oldest. And one of the hypotheses that we are trying to test is that the lake that once filled Jezero wasn't there just once, but that it went through multiple episodes of filling up, drying down, and filling up again. This is very important because it means that we will have multiple time periods in which we could potentially learn about environmental conditions on Mars. And we also have multiple time periods when we might be able to look for evidence of ancient life that might have existed on the planet. This is a hypothesis, but we've started to acquire information that bears directly on it. And if I could have the next image. This is an image taken with the SuperCam RMI camera. This is essentially a telescope mounted on the rover. And it's of a region that we call R2b. It shows a small hill or a small cliff, several meters across, of very finely layered rock. This is exciting to us because the simplest interpretation of these rocks is that they represent fine-grained rock deposited on the bottom of a lake. In other words, mud that might have been deposited and turned into rock. This is exactly the kind of rock that we are most interested in investigating for looking for potential biosignatures in this ancient rock record. If I could have the next image. Now we have driven to this locality that you see in front of you. This is the area where we are really going to be digging in, both figuratively and literally, to understand the rocks that we have been on for the last several months. Actually, ever since we landed. We have been on rocks that we call the paver stones, and those are the whitish rocks that you see in this image. We've been studying these in detail for some time, trying to ask and answer this most simple question. Are these rocks volcanic or are they sedimentary? We've been talking about that for a while, and I'll tell you we still don't have the answer. But I want to tell you why we don't have the answer. If I could have the next image. This shows you what we are up against. This is an image that is taken with the Watson camera, which is mounted on the robotic arm. This camera extends out to a few centimeters off the surface of the rock and takes close-up pictures. So this is a few centimeters on a side. What you are looking at here has an exquisite detail, but what we are seeing still doesn't answer the question, volcanic or sedimentary, because there are confounding factors. So one of the things that you can see in this image is dust. Dust coats essentially all of the rocks in our study area. It's what gives this image its reddish tint. You can also see little sand grains and pebbles. These are presumably brought in from somewhere nearby, but don't have necessarily anything to do with the rock below. And perhaps less obvious, but of considerable interest, is what appears to be a purplish coating on the smoother surfaces of this rock. So all of these factors conspire to prevent us from peering into the rock and actually seeing what it is made out of. So this is a reason we have not been able to answer this question, igneous or sedimentary, but we have a potential solution. We're very excited to deploy for the first time our abrasion tool. So much like a geologist, when they go out into the field, they take a hammer, they will break open every rock that they want to study, and they will look into it. Well, we don't have a hammer, but we have an abrasion tool. And if I could have the final movie. This is a movie taken from the test bed prior to launch. And what you see is mounted on the robotic arm, an abrading bit that is grinding into the surface of the rock. And it's producing a smooth patch that is about a centimeter into the rock. And then we will pull the abrading bit out, and we will blow compressed air to blow the dust away to yield a smooth, dust-free surface that we can then deploy our instruments on. This will allow us to see through all of these confounding factors, and to really, I'm pretty confident that we will be able to answer this question, volcanic or sedimentary. We actually commissioned this capability just within the last few days, and we will deploy it for the first time and get our instruments out onto those surfaces in the coming weeks. So it's a very exciting time because we will now actually get into these paver stone rocks, both with the abrasion tool and with our scientific instruments. And then we will also take our first sample, this really important step in meeting the mission's goals of collecting a suite of samples that are worthy of return to Earth. And to tell you more about the science campaign that we are doing and our sampling, I turn it over to Vivian Sun.
Great, thank you, Ken. So yeah, I'll be talking in a little bit more detail about our first science campaign and what we're doing to prepare for getting our first sample. So as Dr. Zurbuchen mentioned at the beginning, this sampling process is actually one that began many, many years ago when the science community got together and discussed if there were samples from Mars that we could return and study in our laboratories here on Earth, what are the best types of samples that we could get that would really give us the best understanding possible of Mars and its history? And so those early discussions were, of course, really influential in our decision to even go to Jezero in the first place. But also, those discussions were really helpful for guiding our planning once we landed and even before we landed. And so as Jennifer mentioned, planning the science campaign and this mission is really like planning a road trip, as you would here on Earth, except that we're on Mars. For example, we have a destination, we have a set amount of time in which we want to do this campaign. And we also have a lot of points of interest that are nearby or along the way to our destination that we really want to go and see. And the challenge, as always, is figuring out exactly where we want to go and how we're going to fit everything into our schedule. And then once we're on the road, as we are now, we're continuously adapting and adjusting our plan based on new information that we get. And so this is kind of the process that the Perseverance team has been going through for the past months and years. And if we pull up the first graphic now, you can see that we, ever since landing at the Octavia E. Butler landing site, shown here in the green text, we have a destination for this first science campaign, which is to get to the delta. And that's indicated in this image here by that point labeled 3 Forks, and you can see the delta in the top left corner. Along the way in our campaign, of course, we also have these different areas of interest that we're going to, and those are the 3 areas labeled at the bottom: the crater floor fractured rough, Sita South, and the raised ridges. And these are the regions where we're really going to go and do a very thorough exploration of those rocks and acquire samples from those locations. So how did we pick our very first sampling location? Well, where we currently are is by that point that was labeled crater floor fractured rough, about 3,000 feet south of our landing site. And as Ken mentioned, our first campaign is really focused on studying the crater floor of Jezero, which is the majority of that image, basically everything that wasn't the delta. That isn't the delta, and there are 2 major units that we're interested in studying in this crater floor area. And so if we look at that image again, on the right side of the image, this is what we have been calling the crater floor fractured rough, which is again going to be our first sample. And this is the cratered terrain, very kind of similar to the terrain that you see on the moon with all of its craters. And then in the middle, as we've mentioned, this is the region that we're calling Sita, which is this lighter toned rock that's covered by a lot of sand and dunes. And so these are the 2 major rock types that we're really investigating in this first science campaign. And as Ken mentioned, this crater floor fractured rough unit is a mystery to us, because even though we have been on this unit since landing, we still don't know if it's an igneous rock like a volcanic flow, or if it's a sedimentary rock that was deposited by air or in water. And of course, understanding the origin of this crater floor fractured rough unit is going to be critical to not only reconstructing the history of this lake that used to be here, but also it's important for understanding just the geologic history of Jezero, as well as the area around Jezero in this region of Mars. And so what are we going to do once we get to our first sampling site? And again, we're currently at that crater floor fractured rough point on that map, and this is roughly in the area in which we anticipate our first sample. And so now if we pull up the second image, you can see a picture of actually where Perseverance is currently sitting right now on Mars. And in the foreground here, you can see those lighter colored paver stones. And then in the background, you can see these kind of higher standing, more rubbly parts of the crater floor. And again, both of these different types of rocks are part of that crater floor fractured rough unit that we're studying. And so once we get to our first sampling site, the very first thing that we're going to want to do, and you can expect that it'll probably look similar to that image that we just showed, but the first thing that we'll want to do is identify the exact rock in our workspace that we want to sample. And for the purposes of this first sample, what we're really looking for in this crater floor fractured rough sample is really a rock that is kind of prototypical crater floor fractured rough. And what we mean by that is we want this sample to really kind of summarize and record the history of this entire unit as much as possible. We want it to be representative of this unit. And so that means that we're going to be looking for things like texture and chemistry and mineralogy, and we'll want our ultimate sampling, our sample rock, to have kind of the typical texture, chemistry, and mineralogy as all the other crater floor fractured rough rocks that we have explored and seen so far on our trip. So after we pick the exact spot in our workspace that we want to sample, the exact rock, one of the first things that we'll do is actually kick off a series of very choreographed and coordinated events. And the series of events is going to be the same as for every sample that we're going to acquire. So one of the first things that we'll do is abrade, and as you saw in Ken's video, that abrasion is really helpful for removing the superficial dust and any surface coatings on these rocks. And hopefully by seeing these finer scale details, like grains and crystals in the abrasion patch, hopefully that'll give us an answer to whether these rocks are igneous or sedimentary. But so after doing that abrasion, we'll then proceed to core a different part of that rock. And the core itself is going to be about the size of your finger, and the rover will acquire the core, and then it will process that sample in the tube. It will seal the tube, and then it will store that tube inside the rover belly until it is time to drop off that sample on the surface of Mars for the sample cache that will eventually be returned back to Earth. And so that was just a really quick summary of what we've been up to in our first science campaign. And I think it's safe to say that we're all just incredibly excited to be, on the cusp of getting this first sample from Mars, from another planet. So we're just incredibly excited, and we can't wait for it to finally happen. So with that, I'll hand it off to Olivier Toupet, who's going to talk to us about the Perseverance rover's autonomous driving capabilities, which is really what is enabling us to do all this fantastic science and sampling.
Thanks, Vivian. I'm now going to talk about an exciting new technology which has recently come online on Mars, on Perseverance this month, and which has already enabled us to make a lot of progress on our science campaign, as Vivian explained. And that's something that we call autonomous navigation. Now, you may be familiar with the self-driving cars on Earth. Those are relatively new and quickly gaining popularity. But we at JPL have been using autonomous driving on Mars for over 2 decades now. It all started with the Sojourner rover in 1997, which had basic autonomous driving capabilities. And then those capabilities evolved with the Mars exploration rovers, Spirit and Opportunity, in 2006, and then with the Curiosity rover in 2011. And now, finally, as of this month, that capability is active on our latest Mars rover, Perseverance. While self-driving on Mars isn't new, we completely redesigned the artificial intelligence, or AI, software to make it much more capable for perseverance. In particular, the rover is now able to straddle large rocks, something that no rover could do before. And all the complex onboard decision-making and path planning is now happening as the rover is driving, which means that Perseverance is able to drive much faster than the other rovers. Those other rovers had to stop, take multiple images, then process those images, and then find a safe path forward, and only drive about 3 to 4 feet of that path before having to stop again and repeat that process. So that meant that those rovers were spending actually more time stop than driving, which meant a much slower traverse in autonomous mode. This is no longer the case with Perseverance. Autonomous driving is now just about as fast as human-directed driving. So let's show our first video. There you can see the Perseverance rover driving itself in our Mars yard here at JPL through pretty challenging terrain filled with large rocks. And this is one of the many tests we conducted over the past 5 years that we spent developing this new technology. So how does AutoNav work? At a high level, the AI software builds a 3D map of the environment around the rover using images taken by the stereo cameras of the rover. You can think of those as the eyes of the rover. And then smart algorithms generate a path that is optimized to bring the rover to the goal as quickly as possible while avoiding any obstacle on the way and keeping the rover safe. So why do we use autonomous driving on Mars? So let's show the next image. Here you can see all the driving Perseverance has done on Mars since landing in February. And the autonomous drives really stand out in the bottom part of the image because they are much longer than the drives conducted by human drivers. And so why is that? Well, human drivers are limited to driving only on terrain that is visible on the images that the rover sent back to Earth. We can't drive on terrain that we can see. That would be too dangerous. And we also don't drive the rover in real time. So to explain that a little bit, the way this works is that the Surface Ops team meets here every day at JPL, writes all the commands for the rover, then at the end of the day, we send all those commands at once to Mars, the rover receives them, and then executes them all overnight while we all sleep, and then sends the data back the next morning, and then we start a new planning cycle. And so that means that the human pilots can only drive at most 100 to 150 feet every Martian day, depending on the local geometry of the terrain, because of course, if you have large boulders and hills, those create occlusions, you can see behind them, and that further restricts how far you can go. However, with autonomous driving, the rover is able to take new images as it drives and generate new paths to avoid the newly detected obstacles. So it can really drive itself for however long we allow the drive to last. And as I explained, our autonomous driving is also much faster than before. And so that resulted in Perseverance accomplishing the longest ever autonomous drive on Mars. And that was just on the second day that Perseverance drove itself. So let's show the video of that record-breaking drive. And you can see there images that we collected every 5 meters. So I apologize if it jumps a little, although I'm not seeing the video. Okay, there we go. So something that's pretty cool. Oh, I guess we have technical problems. Well, I was going to say something that is pretty cool in that video, maybe it will be posted on the website, is that you can see at the beginning of the video the Perseverance rover driving by the Ingenuity helicopter during its autonomous drive, illustrating how our AI software is able to not only avoid obstacles in the natural Mars terrain, but also man-made helicopters from Earth. But the important takeaway message here is that with autonomous driving, we're able to cover a lot more ground, and that means making a lot more progress towards the science campaign desired destinations. So I want to show one last image, which is a nice mosaic taken by the Perseverance rover at the end of an autonomous drive. And you can see there in that image the tracks of the rover, which show the path that was picked by the AI brain of the rover during the autonomous drive. And that's something I found really exciting about every autonomous drive, is that you never know what path the rover is going to end up driving on Mars. And as a rover driver myself, I can talk a little bit about that. The way this works is that we pick waypoints that are pretty far apart, and then we just send a go command to the rover, we say, go AI, and then we patiently wait for the rover to call back home and tell us how the drive went. So it's a really thrilling experience. You can picture me waking up early in the morning and waiting anxiously for the data to arrive on Earth and discover how the drive went, where the rover drove. And so it's also a little bit nerve-wracking, if I'm being honest. But so far, the AI software has performed extremely well. And I look forward to seeing Perseverance continue to drive itself successfully on Mars, push the limits of how far it can go and how difficult of a terrain it can traverse, thanks to our new autonomous driving software. And with that, I will hand it back to Jari for the Q&A session.
Okay, thanks, Olivier. So I know we had a little bit of a technical issue there. Just know that we are going to put all the images on our website, so you could go to mars.nasa.gov/perseverance, and the websites will be played again at the end of this briefing. Okay, so now we're going to head into Q&A. Just a reminder for members of the media on the phone lines, press *1 if you'd like to ask a question, and if you're on social media, the hashtag is AskNASA. Okay, we're going to head first to the phone lines, and our first caller is Robin Andrews from the New York Times. Go ahead.
Covering the rocks up at the moment, but has there been anything geologically speaking that has either confounded or just surprised the science team?
Ken, would you like to take that?
Yeah, I'll start. Probably the most surprising thing that we have seen so far is when we look at images of the delta, this feature that brought us to this location indicative of a lake, we see clear evidence that there was indeed a lake. There was a period when the water level was quite high and the lake was, the delta was expanding out into the lake, a relatively quiescent period. But we also see higher up, and this you can only see from the ground, you can't see it from orbit, is that higher up and therefore younger, there was a period of lower lake level and flooding, what might have been flash flooding, moving large boulders across the top of the delta. And this is suggesting, as part of what I indicated earlier, that there are multiple phases in which this lake was active. So that's an especially interesting aspect to this environment, that it might record multiple events that were not obvious at all before we got there.
Great, okay. Next in the queue is Bill Harwood from CBS News.
Yeah, hi. Yeah, a quick question for Ken, if I can just follow up a minute. I'm a little confused about the nature of the crater floor, where you have rocks that you can't really tell are sedimentary or possibly volcanic. I would have assumed that the floor of a lake bottom would feature sedimentary deposits by definition. So, I mean, can you talk a little bit about what it would mean if they are volcanic rock there? I mean, I don't understand the history of the presumed lake and volcanic possibility. Thanks.
Yeah, this is a great question, and I would say that the null hypothesis, the thing you start off with is, we are in a setting that we know once had a lake in it, therefore the first thing you should be thinking is these are sedimentary rocks. That is a good idea, but it needs to be tested. And as I indicated, we have been struggling to apply those tests in a way that is definitive about whether they are lava flows, this crater floor fractured rough that Vivian referred to, or what I call paver stones. Nevertheless, either one is a very interesting result, and let me explain why. If the crater floor fractured rough unit is in fact a lava flow sourced from a vent that we have not yet identified, that's really important for our understanding and especially for sample return, because one of the special things about volcanic rocks is they can be dated back on Earth with very high precision and accuracy. So one of the things we would be particularly excited about if we found that it was a volcanic rock is to get a radiometric date that really pins the timing of many of the things that we are looking at on Mars. So either way, it's interesting, and both are possibilities.
Great. Okay. Next reporter on the phone line is Alexandra Whitsey from Nature.
Hi, thanks for taking my call. My question is for Vivian Sun. Again, just staying on this crater for fractured rough, if this is likely to be where we're going to see our first core, can you talk a little bit more about, what is its texture like? Does it remind you of any particular rock units on Earth? Does the nature of the CFFR unit change as you've driven over it for a kilometer or more?
Oh, thank you. That's a great question. So yeah, there's a lot to unpack there. So this crater floor fractured rough unit, in terms of the different textures, as Ken mentioned, one of the things that our science team has been discussing in a lot of detail is determining whether these are igneous or sedimentary rocks. And so I think comparisons can be drawn, from what we can see currently on these crater floor fractured rough rocks. They can be drawn to various rocks on Earth, kind of in both settings. So it's a little bit difficult to say exactly what the nature of these rocks are. Hopefully, by doing the first abrasion, we'll be able to get a closer look at the interiors of these rocks, and hopefully that will be less ambiguous. But in terms of the different textures of the rocks, I alluded to this a little bit, but you can see in that second graphic that I had, we have these flatter kind of paver stone rocks in front of us where we currently are. And then in the background, you can see that there are these kind of higher standing parts of the crater floor fractured rough unit. And so this is something that we're still continuing to investigate with the mission, is figuring out, is there any difference between these two different types of rocks that are both in the crater floor fractured rough unit? And if so, what might those differences mean?
Okay. All right. Next caller on the line is Issam Ahmed from AFP. Go ahead.
Hi. This could be for Ken or for Vivian, I suppose. You've spoken about the sort of searching for these biosignatures, and I understand that nothing will ever be confirmed until we have the sample return mission. But when do you think you might get some at least sort of sense or idea that if something looks promising amongst samples for having biosignatures?
Yeah, I'll take that one. The potential biosignatures that we can see with the rover are primarily with the instruments that are on the robotic arm, Pixel and Sherlock, which measure elemental composition, so the chemistry of the rock, the mineralogy of the rock, and also mapping of organic matter. And the first opportunity where we could see potential biosignatures in a way that I think could be compelling will be when we expose the interior of the rock through abrasion. And our first opportunity to do that is in association with the collection of this first sample in the next few weeks. The rock that we are looking at, as you have gathered, we are still puzzling over. But some of the rocks that we see in the area that Jennifer referred to called CETA, and I showed you images of a rock that may be similar with those fine layers, if those in fact are lake muds that have been turned into rock, those are a very prospective place. Those are a very good place to look for biosignatures. And yeah, that image there is showing you the area that we might imagine to be lake muds. And so I think that area is in the near term, this is at least a few months out before we get to this outcrop, is an area that we will be looking very closely for potential biosignatures.
Thank you.
Okay, we're going to go to social media for a couple questions. First one will be for Thomas Zurbuchen. There's been a couple of questions on social media. So Pervez on Facebook and David on LinkedIn are asking, when can we get the samples back to Earth?
As soon as possible. That's the answer, right? And how long does that take? And of course, the most important part is that we let Ken and the entire team do the work that they're doing right now, which is to select the samples, get them ready, and either deposit them or bring them forward. The earliest we can go and pick them up is later this decade, 26 or 28, which brings the samples back the earliest in the early 30s. So that's the time frame we expect the samples back on Earth.
Great, thank you, Thomas. Another question on Facebook, and maybe we'll start with Jennifer on this one. Niels Nielsen on Facebook wants to know, how has your path plans for Perseverance changed as a result of what you've discovered since landing?
Well, I think the obvious one is that we thought we were going to land right at the delta. There's a little airstrip there. We thought that was where we were going to be, and we were going to start investigation of the delta. Because of the CETA region and the terrain relative navigation putting us on the other side of that, we've decided that there's a very interesting unit that you've heard about, this unit that we're on right now, where we want to actually drive the opposite direction. We're going south to investigate this area in this first science campaign and get some of these very old samples from this crater floor unit, and then we will transition and go back over to the delta. We'll still take, you can bring up Vivian's slide here. You can see we're going to drive down south, and we'll probably go all the way to South CETA. You can see that location there. We'll collect samples. We'll go back to the original landing site, and then we will put the pedal to the metal with our auto navigation that you heard about from Olivier, and you can see the path that we'll take to get back over to the delta. So that's very different than we thought, but it's a great opportunity to get some samples from this region of the lake bed.
Great, thank you. We're going to go back to the Media Telecom line. So we have Chelsea God from space.com. Go ahead.
Hi, thanks so much. So with these months of observation and all of these new science findings, I'm sure that mission teams have learned so much about this area on Mars that they did not know concretely previously. I'm curious how this new information post-landing has influenced, the planned sample capture sites as you narrow down more general sites into exactly where you're going to be collecting and caching these samples in the coming weeks.
Who wants to take that one?
Well, I'll answer with respect to the sample collection. One of the things that actually Vivian has been leading is an effort to come up with a plan for many months ahead, perhaps until the spring of next year. And what you see in the image, if I can show the image that we've been showing from Vivian, showing our traverse route, you see that there are sites that are indicated where we are very likely to collect samples. So we are discovery driven, but the way we navigate around to make discoveries is to follow the path that you see there. And the expectation is here on the crater floor, over about the coming year, we will collect 4 unique samples, and we will keep them on board. We will carry them to a site which is not yet determined, where we will cache them for future pickup. It's my expectation that this caching will not happen within the next year, and therefore we don't feel enormous urgency right now to think about where it's going to happen because it is pretty far downstream yet.
Okay, next on the phone lines is Passant Rabi from Inverse.
Hi. I wanted to know, given the initial observations of Jezero Crater, could you compare them to the observations made by Curiosity when it first got to Gale Crater and how that speaks to the differences between the two missions?
Do you want to take that one, Ken, or Vivian?
Yeah, I can give that a shot. All right, so that's a really good question, because that's a really interesting comparison where we have both Jezero and Gale Crater. Both we really believe used to host these ancient lake systems. But I think, what we've been seeing so far from Jezero is in some ways similar to what we see at Gale, and in some ways it's not. So for example, thinking back to Gale Crater and what Curiosity's been seeing, Curiosity has seen, just many, many feet in terms of elevation, many feet of these layered rocks that are kind of the hallmark of being in a lake system, a lake and river system. And so we see these, very finely layered rocks, and there's variations in the layering that tells you about the depositional environment and the pace of the water that deposited those rocks. And when we think about that in the context of Jezero, though, you can see from a lot of the images that we've seen so far of the crater floor fractured rough, there's not a lot of layering in these crater floor fractured rough rocks. There are some kind of on the boundary between the crater floor fractured rough and the CETA unit, as shown in Ken's images showing that layering, that are kind of new data and that we're still digesting. But for the majority of our traverse, these layered rocks in the crater floor fractured rough have been kind of hard to come by. So that's an interesting contrast between what we've seen at Gale with those many layered rocks and the lack of layering in the crater floor fractured rough. But one surprising thing I think that we've seen since we landed is getting a closer look at that CETA unit that's kind of that we're kind of skirting around the edge of. And from orbit, when we look at this unit, we can't really see at the scale of the orbital data. We can't see any of the layering in this rock. And so when we did land and we did put our cameras out to the CETA region to really see it up close for the first time, I think we all were very happily surprised to see, there are layers in that unit. And so, of course, that might spark some more comparison with Curiosity and what it's been seeing at Gale Crater. So hopefully we'll be able to get more up close and personal with these rocks to really make that comparison better.
Great. Okay, we're going to go back to social media. And a reminder for the folks on the media on the phone, again, if you want to get into the queue, you press *1, and the hashtag is Ask NASA. So this is a question for Dr. Zurbuchen. Darren on YouTube asks, how would this science help future humans on Mars?
So we already heard about some of the technologies that are being developed, and especially you talked to us about the MOXIE experiment, right, earlier, which is all about making breathable oxygen that is there. So there's tangible, actual technologies that really help support life once we're there with humans that are being proven right now, both on the landing side, on the navigation side, but also that particular experiment. I think secondarily, what we're really doing with this particular, explorer is really look at the entire environment, both, remember there's a weather station that it's carting around with, but also really looking at the best science that, of course, humans could do as we get there. So really understanding what Mars is like right there with all dimensions, but learning also how to take advantage of the resources are the most important factors of how it supports human exploration.
Great, thank you, Thomas. This is a question, I'll start with Ken, but if other people have ideas, you can feel free to chime in. Ciencia News on YouTube asks, what is the most exciting thing found by Perseverance to date?
I would say two things. The first is the very compelling demonstration of the helicopter ingenuity, and I'll let others speak to that. It is remarkable what that helicopter can do, and I think it's going to be, in the future, it will be transformative to have a helicopter element for science investigations. The other feature, which is a direct scientific observation, is the one that I alluded to, that quite different from Gale, we see evidence of rapidly flowing water, a phase of rapidly flowing water in this lake late in its history at the top of the delta, after the lake had dried down substantially. And this fits into a larger picture of the way Mars may have evolved from a period when lakes were relatively common on the surface to a period that is younger when there were periodic outflow events. We don't know exactly how those happened or why they happened, but we are starting to see evidence, and later in the mission, we will actually be up on those rocks and be able to explore them directly.
Okay, we're going to go to another social media question. This one is about navigation, so I'm going to alter it a bit because Olivier was talking about how much we can do with the autonomous driving there, and so let's see, where did it go? Oh no, I lost it. It's, okay, sorry about this. There we go. Okay, Mars Hub on Facebook asks, is Perseverance programmed to drive and do a lot of things itself, or do you control it from Earth? How much are you guys doing from Earth?
That's a good question. So there are various modes of autonomy, various ways we can drive the rover. One is to actually give it low-level commands and say, Perseverance, please turn your wheels that much to make forward progress, backward progress, turn in place. And so we can really control the exact motion that the rover does. But as I explained, when we control it that way, we can only drive in the terrain that is visible right around the rover, so we can't go very far. And then there is more advanced modes of autonomy where we can say, rover, please drive to that waypoint, and we can choose where to place that waypoint on Mars. And then the rover can either drive just the fastest path to the goal without imaging, and so without avoiding obstacles in the terrain if we think the terrain is very benign, or it can actually image, detect obstacles, and by itself decide to swerve in between obstacles to get to the goal. Another autonomous capability I haven't mentioned, which is new with Perseverance, is that at the end of the drive, once the rover reaches the goal, in order to be able to talk back to Earth, it needs to turn to a heading that enables it to talk to the orbiter. And in order to do that, we actually do that autonomously, because at the end of an autonomous drive, as I hinted at earlier, we really don't know where the rover is going to be, what is going to be the final heading, what is going to be the final location. And so the AI software is actually able to look at a table that says, hey, given my current tilt, I need to turn at that heading to be able to talk back to Earth. And if it cannot, because there's an obstacle, then it's going to keep on making progress towards the goal until it finds a place where it can turn for COM, is how we call it. So that's about the extent of the autonomy for the driving side. And of course, there is also some autonomy for the robotic arm operations. But that's probably a different topic.
I think we should take. Sorry, okay. All right, so we're going to go back to the phone lines, and we have John Amos from the BBC on the line. Go ahead, John.
Hi, thanks very much for doing this. Can I just talk about the sampling strategy for a moment, if I may? Ken mentioned, maybe 4 samples over the next year. I mean, I just wonder if you get to somewhere like R2B and you look at that stretch of rocks, which I think is about 20 meters across, something like that, and you look at one end and you think, wow, well, we ought to take a sample from there. But then you look at the other end of it and you think, I don't know, what about the other end? Would you conceivably take 2 samples at a location? Or are you restricted by the number of total tubes you have, so you have to make a choice, one place or another?
Yeah, so I can take that one.
Go ahead, Vivian.
Yeah, that's a really great question, because I think you're hitting on some of the complexity that we work with when we are planning these missions. And as you mentioned, there's a limited number of tubes, so we have to make our choices about what rocks to sample very, very carefully and with as much information as we can have. So I think an important thing to mention is, as Ken mentioned, we are planning with this first campaign. Our going-in plan is to collect 4 unique samples from those 3 areas, the crater floor fractured rough, CETA South, and the raised ridges. But it's also important to keep in mind that this is our plan based on what we know. And as I mentioned, we're always continuously adapting and adjusting our plans based on new information. And so I think as we progress in this first science campaign, as we get more of a better understanding of what these rocks are and what the environment at Jezero was like, we'll always keep in mind that that plan can be adjusted and adapted based on that new information.
Okay, next on the line, we have Katrina Miller from Wired. Go ahead.
Hi, thank you. So it was said that Perseverance could drive about 100 to 100 feet per day with human pilots. And I'm not sure if I missed this, but what was the distance of the longest AI-powered drive so far? And is there ever a time or situation when manual driving would be better or more beneficial than the autonomous driving?
Olivier?
That's a great question. Indeed, in the terrain that is visible around the rover, we have the choice to either drive manually or just turn on AutoNav and let the rover drive itself. That's always a little bit of compromise, and recent experience has shown that actually we've been more successful letting the rover drive itself than trying to micromanage the path, because what happens is that sometimes the rover is going to slip and deviate from the expected path. And if it's not autonomous, then it's going to keep on deviating, and sometimes it may drive over a large rock or end up faulting the drive because, for example, the suspension angles are not what we expect, and so we have reactive checks that will safely stop us in that case. However, in autonomous mode, the rover is able to image, is able to see all the rocks, every 3 or 4 feet. It's able to reassess the situation and plan a new safe path. So it's actually been doing really well that way. And so far, again, we just started using autonomous navigation, so we don't have a lot of miles under the wheels. But so far, we've driven about, I would say, 3 to 4 times longer distances than when human drivers pilot the rover. But we expect those distances to grow much more in the future as we are able to drive for longer on Mars. And so I think you will see probably drives that are going to be, 3 to 4 times our longest drive so far, which is about 350 feet in the next few weeks or months. And in fact, in the future, we'll even be able to do what we call multi-sol AutoNav, where the rover is able to drive itself on Mars and stop, and then the next day resume its autonomous driving, and then stop and go on like that for several days. So we expect to be able to break a few records in terms of longest drive on Mars in history. So I'm very excited about that.
Great, thanks. Oh, thank you. All right, so we have a little time, so we're going to keep going. Next on the phone lines is Ken Kramer of Space Up Close. Go ahead.
Hi, thank you for doing this and a great mission so far. My question is, I think, for Vivian, please. Can you talk a little bit more about how you're going to use the science instruments to select the samples, which ones you're going to use, how long do you need to operate them? Thank you.
Yeah, absolutely. So I think the short answer is that we're really wanting to use all of our science instruments and our payload on board to get as much data as we can, even just in the preparation for sampling. So acquiring as much data as we can of these rocks so that we can inform our decision about exactly which rock to sample. In terms of getting into a little bit more detail about the instruments, I think we have a fantastic suite of instruments that really complement each other in terms of their functions, and they really help us put together, an efficient plan for getting to that sampling decision. So, for example, we have instruments like SuperCam and MassCam that are on the remote mast, and we call them our remote sensing instruments because we can be at a distance from the rocks that we're actually observing. So MassCam Z takes these fantastic images at very high resolution that helps us really do at the same time a kind of survey of the rocks around us, covering a lot of area, while also letting us see kind of those finer level details like kind of the textures of the rock and any layering in the rock. We also have SuperCam on the remote mast, which is helping to get at the composition of these rocks, so things like the chemistry and the mineralogy of these rocks. And similarly, we use that in a surveying fashion as well. And we also have our engineering cameras, of course, that we use every single day to give us the full context of the workspace that we're in. And then all these remote sensing instruments are really helpful for complementing the proximity science instruments that are mounted on the arm of the rover. And these are the instruments that we place much closer to the rocks. And so in that second image that I had, you could actually see the robotic arm reaching out and hovering over the rocks in front of us in our workspace. These instruments, because of how close and proximal they get to those rocks, they really give us really the highest resolution data possible. And so we're able to see really fine scale things like grains and crystals, especially once we are able to abrade. Also at that scale, we can get these chemistry maps as well as these mineralogic maps. And so getting that really high level detailed look at these rocks up close is also incredibly helpful, as you can imagine, for coming to an idea of not only what these rocks are, but also just what rocks do we want to sample in our workspace.
Thank you.
Great. Okay, we're going to go back to social media. So I think I'm going to throw this one to Ken. Stephen Tendrick on Facebook says, Mazel Tov, are we expecting evidence of ancient sea life?
Ancient sea life?
Yes.
Well, so one interesting thing about Mars is we don't know whether there was ever a phase when there was an ocean. It is a matter of debate. But it is clear that the place we are looking at in Jezero Crater was not part of a sea. It was a lake, and it was a lake that was about 40 kilometers across. So we are not looking for things that would have been growing in the sea. And the other important aspect of this is that we are looking very, very far back in the history of the solar system. And what that means is that life would not have had much of a chance to advance very far. And that's why we always say that we are looking for evidence of potential microbial life, because on Earth, our example of one about how long it takes life to evolve, on Earth, advanced life, which you might consider to be sea life, like fish and corals and these sort of things, they didn't appear until relatively recently. So we are peering very far back in the history of life, and we only expect, if there is life, that it would be microbial.
Did you want to add to that, Jennifer? Or?
No.
Oh, okay.
I think Ken handled it very well. Yeah.
Okay. Next on social media, I think I'll toss this over to Thomas. Alimsha on LinkedIn asks, if samples are tested under laboratory conditions on Earth, how will this affect accuracy?
Well, that's exactly the question at the heart of this, right? We bring these samples back to Earth because we can make them as the measurements as accurately as humanly possible here on Earth. That every year the technologies are getting better. And as we bring these samples back, and we said in the early 30s, these samples will be here, we have the best technology available to actually make these measurements. They're by far better than the technologies that we have today, if history is any teacher. So it will affect it tremendously and in a positive fashion.
Great, thank you, Thomas. Juggernaut Joe on YouTube asks, what place has the highest probability to have preserved fossils that we could find if they exist on Mars, the delta or the crater floor?
Well, I'll give my answer. This would be a matter of opinion at this point, because it depends completely on what the environment was that is recorded in those rocks. And if the rocks that are in the crater floor, and in particular, for example, in that area that I called Artubi, or in the area that we called Sita, if those are former lake muds, those are a very good place to look for fossils, for what we call biosignatures. The delta may also have such environments, but it's also clear that some parts of the delta were fast-flowing water and sand and rocks. And just even intuitively, you could imagine that the ability of a rock to preserve evidence of life, if it is mud that deposits very smoothly and slowly and without much agitation, there's a good possibility of preservation. If you're in, say, a mountain stream with boulders rolling along, not a good place for preservation. So that's the kind of criteria that we will use, but we can't really apply it all that well just yet.
Great, thank you. All right, so this is a question for Jennifer. Sakshi on LinkedIn asks, what was the most challenging part of building this Mars rover?
Wow, how much time do we have? No, I think the key here is that there are thousands of people who contributed to this, and every person had a depth of knowledge and or a breadth of knowledge that that brought something unique to the team to be able to build this rover, this helicopter, and develop this science mission. And so there's nothing, the landing system is always harrowing because it's got to work and there's only one way to get to the surface. So obviously that's one of the challenging things. But I think in terms of the upgrades that we've made over time, I've worked on all of these rovers and all of these missions. And a real complex and difficult to operate and manage system that we built on this was the whole sample caching system and the adaptive caching assembly. I mean, we added, we had 3 robots. We have the big robotic arm on the outside, which Curiosity had. We have the bit carousel now that we use to transfer samples and tubes back and forth in bits. And then we have another robotic arm on the inside that manipulates these tubes and uses force sensors. And there's just a lot of complexity to that. And even over the last few weeks, we've been understanding the complexity. We had a couple first-time activities that we tried once, and we had maybe a thermal issue of some modeling we didn't quite understand, and then we tried it again, and we had a timing issue with the motor controller. So we are learning as we go. It's a complex system, and I think that adaptive caching assembly is really kind of the paramount thing that we've done on this mission that's much more difficult than previous.
Okay, and Lyra on LinkedIn asks a question, maybe this is a question for Ken or Vivian. How will texture of these rocks be analyzed if you use the abrasion tool?
Sorry, could you repeat the question?
How will texture of these rocks be analyzed if you use the abrasion tool? I think, how do you analyze it after you've rubbed things away from it?
Okay. So we abrade off the surface, we get rid of the sand and the dust and the coatings, and then with compressed gas, we blow all of the tailings away. And so this would be, it would not be quite as polished as your countertop, but it is the same kind of idea. It's a nice flat surface, and it will be recessed below the surface of the rock by maybe that much, so not very far. And then we bring the instruments in and they look directly at this new surface. And this is exactly the way these instruments were designed to function. It's what we have always been assuming that we would need to do to get rid of this confounding superficial artifacts, basically.
Okay, we'll take one more question on social media. I think this is probably a question for Jennifer. Elizam on LinkedIn asks, how deep does the drilling process go? How many attempts do you have to drill before the cutting tools become dull?
Great question. We go down, about 5 centimeters, and in general, we have several bits that we've brought along with us, and we will look at the abrading bits and we'll inspect them and we'll see. It really depends on the kind of rocks we're up against. If we have very soft rocks, a bit may last a very long time. If we have very hard rocks, we may have to change out the abrading bits more frequently. And so that's something that we monitor. The team is very adaptable to those types of things. We basically have designed the system to be able to manage around whatever we find relative to the bits. And so I think time will tell how we do with that.
Okay, there's much more mission ahead, and so we're going to wrap this briefing. If you want more information about the Perseverance rover, we've got plenty of it online. You can go to nasa.gov/perseverance and mars.nasa.gov/perseverance. The rover is also constantly sending down raw images to us, and you can check that out at go.nasa.gov/perseverance-raw-images. You can also follow our journey on social media at NASA Persevere. Thanks very much for joining us, and go Perseverance.